So just imagine spending like 3 solid weeks of your life sourcing random bolts from 3 different continents.
Oh, yeah. The endless tracking numbers.
Right. And you're crimping these tiny, tiny wires until your fingers literally ache.
The worst.
Tuning lines of code for hours, all just to realize, well, you could have bought a machine that does the exact same thing right out of the box.
Yeah, but where's the fun in that?
Exactly. Welcome to the ultimate dilemma for the advanced 3D printing enthusiast. And, you know who you are. You listening to this, you've moved past that beginner phase.
Oh, totally.
You've mastered printing PLA without even breaking a sweat. You've probably spent, I don't know, weeks dialing in your PTG profiles just to eliminate that awful strip.
Getting those retraction settings just right.
Yep. You might have even built one of those makeshift enclosures out of acrylic just to keep the drafts away from your printer.
The classic IKEA lac table build.
Exactly. But now, you're hitting a wall. You want to print these advanced high temperature materials.
Yeah, the technical stuff.
Right. You're looking at complex CAD models and you realize, I actually need soluble supports to make this work. You want flawless geometries, and that reliable little starter printer you have it cannot keep up anymore.
It is. I mean, it's a very familiar crossroads for the intermediate hobbyist.
Yeah.
You reach this point where you have to evaluate not just what you want to physically produce, but, how you actually want to spend your weekend hours.
Yeah.
And the market right now is essentially split into 2 totally extreme directions for this next tier of printing.
And exploring those 2 directions that's our mission for today's deep dive. We are digging into 2 highly detailed sources to help you make this massive decision.
It really is massive.
It is. First, we have a Monday Hub article that just completely deconstructs the original Prusa XL and its whole multi-tool setup.
A really fascinating read.
Yeah, and on the other side of things, we have a Thursday support piece asking a very, very relevant question for anyone with a toolkit. Is building a Voron 2.4 still worth it in 2026?
Which is such a valid question right now.
Right, because these are 2 completely opposite philosophies fighting for the exact same premium spot on your workbench.
They really are. I mean, they represent a fundamental choice about workflow and independence. We are not just, comparing stepper motors and heated beds today. We are looking at what it actually means to be a creator in a hardware ecosystem that is, it's rapidly changing.
Okay, let's unpack this, because before we even look at the physical hardware specs, we have to understand the ideology behind these machines.
Absolutely.
Starting with the Voron 2.4. So this is an open source CoreXY printer. The original design was released, back in May 2020 by the Voron design team.
Yeah, founded by Max Zollin.
Right, Max Zollin. And we need to be abundantly clear about what this machine actually is, because it is not a plug-and-play kit.
No, definitely not.
You are not printing with this the same day you get it. It is a multi-week, heavy-duty DIY project. You are building this from a massive bill of materials.
Oh, massive is an understatement. You are sourcing every single screw, every piece of aluminum extrusion, the wiring harness, all of it yourself.
Right.
Or, you're buying a third-party kit from vendors like LDO or Formbot.
Right.
And you are dedicating dozens of hours to the physical assembly alone, just turning wrenches. And then you have to tackle the wiring.
Which can be incredibly daunting for a lot of people.
Very much so.
Yeah.
And finally, you spend even more time configuring the Klipper firmware.
Okay, wait, I want to pause on Klipper for a second, because it gets thrown around a lot as this buzzword in the community.
It does, yeah.
What does tuning Klipper actually entail for someone who is building a Voron?
So Klipper fundamentally changes how a 3D printer processes information. Traditionally, the small main board on your printer is trying to read the G-code, calculate all the physics of the movement, and physically drive the stepper motors all at the exact same time.
Right, which is a lot for a tiny chip.
Exactly.
Yeah.
It gets bogged down. So Klipper takes all that heavy math and offloads it to a much more powerful computer, usually a Raspberry Pi.
Ah, okay.
Yeah, so the Pi calculates the complex kinematics, and it just feeds precise, simple timing instructions down to the printer's main board. But, and this is the kicker, because you are the one building the Voron, you have to tell Klipper exactly how your specific machine is built.
Because it doesn't just automatically know.
Right. You have to manually configure the pinouts. You have to tune the resonance compensation to cancel out vibrations.
Oh, wow.
Yeah, and you have to calibrate the pressure advance.
Yeah.
I mean, it is incredibly powerful, but it requires serious dedication to actually get right.
Which, brings up a great analogy, I think. Buying the Prusa XL is like purchasing a high-end, factory-tuned sports car. You pay a premium, sure, but you basically just turn the key and drive.
Yeah, exactly.
But building a Voron 2.4, that's like buying a giant crate of premium engine parts and a really thick manual with the goal of building a custom track racer in your own garage.
That framing really captures the financial and, frankly, the emotional investment perfectly. I mean, with the Prusa, you are paying for a massive team of engineers in Prague to have solved all the mechanical integration problems for you.
Right, they did the headache part.
Yeah. But with the Voron, you are the chief engineer. If a belt rubs or, a wire shorts out somewhere deep in the gantry, you are the one responsible for diagnosing it and fixing it.
Which is a lot of pressure.
It is. But the flip side of that is that you gain this absolute granular control over every single variable in your machine. You understand it inside and out.
And that DIY philosophy of the Voron, it doesn't just save you money up front, it fundamentally dictates the physical architecture of the machine itself.
It really does.
So let us look at the hardware approaches here. Both of these machines, they both use CoreXY kinematics.
Which is kind of the gold standard for speed right now.
Right. The moving mass of the print head is kept as light as possible because the heavy stipper motors, they stay bolted to the stationary frame in the back. But from that shared foundation, they solve the problem of large format printing in totally, completely different ways.
They really couldn't be more different. So the Voron 2.4, it comes in a few different frame sizes. Typically, you see 250, 300, and 350 millimeters.
Okay.
But the critical design choice here is that it is fully enclosed by default. And if your goal is printing technical engineering-grade materials like ABS and ASA, that heated, draft-free chamber is just mandatory.
You literally can't do it without one.
No, you can't. If you try printing a really large ABS part on an open frame, the ambient temperature differential causes the plastic to shrink unevenly as it cools.
Right, the infamous warping.
Exactly. The corners will just violently warp right off the build plate. It's so frustrating.
Yeah, we've all been there. Now, when I first saw the Z-axis on the Voron, I have to admit, it looked completely over-engineered to me. They call it the flying gantry.
Yes, the signature flying gantry.
Right. So instead of the build plate moving down as the print gets taller, like on most machines, the bed on the Voron is rigidly bolted to the bottom of the frame. It does not move. And the entire XY motion system, the whole gantry, is hoisted up in the air by 4 separate Z motors.
It looks crazy in action.
It does. 4 independent motors just to move the tool head up and down. It honestly feels like you are begging for sinking issues. I mean, why not just move the bed up and down like everyone else?
Well, what's fascinating here is how that exact complexity solves a major mechanical problem.
Oh, really?
Yeah. It allows the machine to automatically and physically tram itself. So those 4 independent motors, they can actually adjust the 4 corners of that flying gantry totally independently of each other.
Oh, I see.
Yeah, so the printer uses its probe to tap the stationary bed. It calculates if there's any tilt or unevenness, and then it uses those 4 motors to physically pivot the entire gantry in the air until it is perfectly, exactly parallel with the build surface.
That is actually genius.
It is. Because when you are printing really demanding engineering materials, a flawless first layer is the literal difference between a successful 20-hour print and a localized plastic disaster on your hoed end.
Right, the blob of doom.
Exactly. The flying gantry virtually guarantees that perfect first layer every single time.
And riding on that flying gantry is the stealth burner tool head, which, by the way, the Voron community developed. It's a fantastic piece of hardware, but at the end of the day, it is just a single nozzle.
Yep, just one.
Meanwhile, the Prusa XL takes a completely different hardware route. It is a fully open frame machine, and it is just massive. It boasts a 360 by 360 millimeter build volume.
Which is huge.
Yeah.
But, heating a build plate of that size introduces huge problems.
Right, the power draw alone.
Yeah, a massive single sheet of aluminum of that size. It takes forever to heat up. It draws a tremendous amount of electricity. And more importantly, it physically expands and bows when it gets hot.
Right, because of the thermal expansion.
Exactly. So Prusa solved this by using a segmented heat bed. They took that giant surface and broke it up into an array of 16 smaller independent heater tiles.
And it only sends power to the specific tiles directly underneath the part you were actually printing, right?
Exactly.
So if you are just printing like a small little gear right in the center of this giant machine, you are not wasting tons of electricity heating the outer edges for no reason.
It's a really brilliant bit of thermal management.
It really is. But having a huge bed is only part of the equation. Eventually, you want to print with more than one material at a time, which brings us to the whole multi-material dilemma.
Oh, yeah. And single nozzle multicolor printing, as we all know, is just notoriously painful.
It is the worst.
Right. If you feed multiple filaments into just one nozzle, you have to flush out the old color completely before the new one starts.
So you don't get those muddy transition colors.
Exactly. Which means the printer constantly travels off to the side, extrudes a massive pile of plastic waste, wipes the nozzle, and comes back.
It takes forever.
It does. You end up with these 16-hour prints where, 80% of your expensive filament just went into a giant purge tower.
And this is exactly where the Monday Hub article focuses its attention on the Prusa XL, because Prusa abandons that single nozzle purge method completely in favor of a physical tool changer mechanism.
Yes.
But we need to be clear on the exact specs here. The XL comes in 1, 2, and 5 head variants. 5 is the absolute maximum option. It is not the standard base model.
Right. Important distinction.
Very important. But the underlying concept is identical across all the multi-tool versions. Each tool is built around their Nextruder design, which means each head carries its own specific filament, has its own nozzle, and crucially, maintains its own independent temperature.
And they just park in this docking station at the very back of the gantry.
Yeah.
So when the G-code calls for a color change or a material swap, the active tool drops into the dock, the carriage slides over, it physically locks onto the next tool and just resumes printing.
It looks like a robot assembly line.
It really does.
Yeah.
You are swapping the entire print head in a matter of seconds instead of melting and flushing all that plastic.
And they also utilize this really clever wipe to infill feature. So instead of building a massive dedicated waste tower on the side, the printer basically hides the tiny amount of transition material inside the hollow infill structure of the model itself.
Which is so smart.
It is. Now, to be completely accurate, this does not mean the Prusa XL operates with literally zero purge or zero waste.
No system is perfectly zero waste.
Right. The nozzle, it still oozes slightly while parked, and it needs a tiny prime line to ensure the internal pressure is equalized after sitting in the dock for a while. But the waste is a tiny, tiny fraction of what a traditional single nozzle system generates.
And that fundamentally changes the economic reality of complex printing. You are no longer throwing away entire spools of expensive filament just to get a dual color logo or to use a soluble support interface.
Here's where it gets really interesting, though. Think about the physics of this. If the XL is physically dropping and grabbing these heavy print heads literally thousands of times during a single long print, how in the world does it handle the mechanical coupling precision?
It sounds like a calibration nightmare.
Right, because if tool number 2 locks into the carriage even a microscopic fraction of a millimeter differently than tool number 1 did, your dual color print is going to have smeared, jagged edges. Are you just stuck manually calibrating all these X, Y, and Z offsets with feeler gauges for 5 different nozzles?
Yeah, and honestly, that was the historical nightmare of older tool changers. People hated them for that exact reason. But Prusa actually solved this by turning the nozzle itself into a highly sensitive load cell.
Okay, how does that work?
So the printer physically taps each individual nozzle directly against the build plate. By measuring the exact pressure and the precise impact point, the internal software just automatically calculates the perfect X, Y, and Z coordinates for every single tool head. Yeah, it completely removes the human error from the offset calibration. It does it all internally.
That load cell technology is incredibly elegant. So, okay, we have the Voron 2.4, this fully enclosed high-temperature powerhouse that you build piece by painstaking piece. And we have the Prusa XL, this massive commercial machine that physically swaps tool heads using automated load cell calibration. How does a listener actually sit down and make a buying decision between these two paths?
Well, we can actually map this out using a very specific decision guide, which is based directly on the workflows highlighted in the Thursday support piece.
Okay, let's hear it.
It requires evaluating what your primary bottleneck actually is. So you should choose the Prusa XL when you specifically need clean dual-color prints, or when you rely heavily on soluble supports and you need to aggressively minimize your filament waste.
Right, that makes sense.
But most importantly, you choose the XL when your primary goal is to pull a machine out of a box, plug it in, and just start a production run, rather than spending 3 weeks debugging a complex mechanical build.
You are basically buying back your time.
Exactly.
On the other side of the coin, you should build the Voron 2.4 when you need a highly repairable, fully enclosed machine designed specifically for warping-prone materials like ABS.
Nice.
But, and this is a big but, you should only take this path if you actively enjoy the process itself. If you treat the multi-week build, all that intricate wiring we talked about, and the clipper tuning as part of the inherent fun of the hobby, then the Voron is deeply rewarding.
If we connect this to the bigger picture, the true value of the Voron is hardware independence. Yeah, you are insulated from a closed corporate ecosystem.
Right.
If a stepper motor fails 5 years from now, you can just buy a generic replacement from an industrial supplier literally anywhere on Earth. You aren't waiting on one specific company.
Yeah, you own the platform.
Exactly.
Yeah.
But the value of the XL is immediate, frictionless access to complex multi-material workflows that would honestly require an engineering degree to build reliably from scratch yourself.
It is a massive financial and temporal commitment either way you go. But, before you pull out your credit card or order a giant box of aluminum extrusions, the sources provided a really highly actionable test that you can literally run this week on your current machine.
Highly recommend doing this.
Yeah, it is designed to prove whether you actually need multi-tool capabilities in your daily life or if you are just kind of in love with the idea of them.
Yeah, we all get shiny object syndrome. So the test focuses on the most practical use of multiple materials, which is printing a model with soluble supports.
Okay.
You are going to run a specific test print using standard PTG for the main object and a soluble material exclusively for the support interface layers.
Now, the material selection here is where people usually mess this up.
Oh, all the time.
You have to use BVOH for the soluble interface, not PVA.
Yes, please do not use PVA.
PVA is just notorious because it absorbs moisture like crazy, but more importantly, it bonds very poorly to PGG chemically.
It just pops right off.
Exactly. It tends to peel off mid-print, which leaves all your beautiful unsupported overhangs to just collapse into a stringy mess on your bed. BVOH, on the other hand, is specifically engineered to form a strong mechanical bond with PTG and nylon.
But the preparation for that BVOH is totally critical.
Right.
BVOH absorbs ambient humidity so aggressively that if you try to print it straight out of the vacuum bag, the moisture trapped inside the filament will literally boil as it hits the hot nozzle.
Which sounds bad.
It is bad.
Yeah.
That creates tiny steam explosions in the plastic, resulting in massive stringing and just a totally failed interface layer.
So you have to dry it.
Yes. You must dry the BVOH at 50 degrees Celsius for 4 to 6 hours before you even attempt this print. It has to be bone dry.
Okay. So once your filament is bone dry, the real trick is managing the thermal delta between these two very different materials because they do not like the same temperatures.
No, they don't.
In your slicer, you need to set the BVOH interface to print cooler, between 210 and 215 degrees Celsius. But you want to keep your main PTG material hot, around 240 degrees Celsius, and set your heated bed to 80 degrees Celsius.
And, because you are using soluble material, you actually want it to physically bond as tightly as possible to the part you are supporting.
Because you're just going to melt it away later anyway.
Exactly.
Wait.
So in your slicer, set the interface contact Z distance to strictly 0.
Zero gap.
0 gap. And use 2 to 3 interface layers just to give it a really solid foundation.
So after the print finishes, you have to actually dissolve the BVOH. You just drop the part into room temperature water.
Yep.
Now, you can use slightly warm water to speed up the dissolving process, but you have to max out around 35 degrees Celsius. If you drop it into scalding hot water, you might actually exceed the glass transition temperature of your beautifully printed PTG part, and the whole thing will just warp right there in the bucket.
That would be tragic.
Yeah.
But the real purpose of this test, right, is to generate real data on your own actual workflow.
Right.
Look at the finished part when you're done. If you find yourself holding that complex geometry and realizing, wow, I actually need this specific BVOH and PTG combination constantly for my projects, then the Prusa XL in your answer.
Yeah, it becomes a no-brainer.
Right. Because
No.
having independent temperatures for the PTG and the BVOH and being able to just seamlessly swap nozzles without purging them through a single hose end, it makes that workflow totally effortless.
So what does this all mean? Well, It means dedicating one evening and maybe 200 grams of filament to this test can genuinely save you from a massive mistake. Because if you finish the dissolving process and realize, you know what, this soluble support trick is just a neat novelty that I will probably only use once a year, then dropping thousands of dollars on a 5-head tool changer is just massive overkill for your workbench.
Total overkill, yeah.
A highly tuned single-head Voron 2.4 is going to be more than enough machine to handle your daily printing needs, while also giving you that enclosed high-temperature capability you wanted in the first place.
It forces you to actually prove your use case with real data, rather than buying based on these aspirational ideas of what you might maybe want to create someday.
Exactly. Well, we've covered the stark ideological differences, the hardware architecture, the reality of these multi-tool workflows, and we've given you a very specific test to run this weekend.
It is a lot of information to process.
It is, but it is really the only way to make an informed choice at this high level of the hobby.
And, this raises a really important question for the broader future of making, I think.
Oh.
Yeah. As these commercial 3D printing ecosystems become increasingly user-friendly, right, but fundamentally closed off, relying on proprietary parts and lockdown software, how much longer will fully open, user-built platforms like the Voron community remain competitive against these highly integrated, automated flagship machines?
That is a fantastic thought to leave you with as you stare down your next big hardware upgrade. Thank you for joining us on this deep dive, and for the full numbers, see printereth3d.com.